coefficients and free terms of canonical equations of the forces method, article 3.4 from the book Mechanical Systems, Calculations of the Marine Facilities. Look, we have the exercise to find the support reactions of the statically indefinable frame. Frame is indicated in the figure 3.4.1 on the left A. So we have statically indefinable frame consisting of two supports A and B, and consisting of the rigid corner and of two rods, vertical and horizontal one, and of the equal elasticity, rigidity of the beams in the frame. So the elasticity, this is elasticity modulus, and this is moment of the inertia of the transverse section for the bending. And we have the external force applied in the middle of the upper beam from the A to the left downward. So to have the support reaction of the system, we is twice statically indefinable. This is very easy to understand due to the in the support A we have three components of reaction, and we have three mathematical equations, three balance equations to determine the reactions of the support for the considered frame. But here we have two more links, so it's not possible to find by using of the by the use of the balance equations. We can do from the assigned system. The main system is loaded by external load assigned F, and loads in the cutoff links in the support B. So the main system is statically definable. So, but to find the support reaction for the main system, we have to have the forces components in the hinge B instead of the cutoff supporting links. So the canonical equations of the forces method for doubly statically indefinable mechanical system has the form, is a form indicated here. So the first equation, physical, is the physical sense of the first equation, that when we substitute instead of the link horizontal and the support B by the force x1 subject to find and making the statically definable main system. So we have to provide in the this point the final displacement have to be equal to 0. So this is equality to 0 of the displacement in the point B when we cut off the horizontal link in the horizontal direction in this point B. So this direction depends on the force x1 we have to apply, subject to find. Force x2 we have to apply the proportionality coefficients. This is a coefficient on behalf of in the direction forced, but the second index indicates the number of the cause of this displacement in the direction force. This is this delta lowercase is factor is a displacement under the unit load. If we assume that x1 is unit load, so the displacement on behalf of x1 would be delta lowercase 1, the same as in the first direction. This would be the displacement of unit load. If we assume that x2 is a unit load, is a displacement delta lowercase 1, 2, the displacement under the unit load x in the first direction under the influence of the force in the second direction of the cutoff supporting links in the point B. And we have as well consider and account the displacement in the first direction under the influence of the external force assigned force F. So they have to be equal to 0. The same equation we do in the determination of the displacement under all the forces in the cutoff direction second in the support B. This is x2. And to use this canonical equations of forces method, which are the compatibility of deformation equations in physical sense, they complement the balance equations to the required number to find 5 support reactions. So we have to find first the factors delta 1, 1, delta lowercase 1, 2, delta uppercase 1, F on displacement under the influence in different direction and the influence of force F external. And as well here we have to find the unit displacements delta 2, 1, delta 2, 2, and delta 2, F appropriately. So to find these factors, we can use so-called rule. We say the Moore integral. The displacement and direction of unit force in direction of connection number unit force in the direction number k in direction the displacement in direction number I delta lowercase ik equal to the sum of the under the sum we have summands. Each summand is integral during each of the segment of the considered frame along the coordinate is coincided with the direction of each segment of frame of the integrator. This integrator is a fraction. In the denominator, we have the rigidity of this definite one leg of frame. We consider when do the sum of this all integrals for all segments of the frame. And this is diagrams of the bending moment for the main system. So if we assume that main system is loaded by in y is loaded by the is loaded by the efforts and force in k direction, we can and we have to find the displacement which is in the y direction. We have to have the diagram of bending moments under the action of unit force in y direction. So when in the in this one fraction in the when we consider the product of in numerator the product of diagrams of diagram of unit force and the action in the direction we look for the displacement of the unit force delta lowercase ik, and under the influence of the efforts in the direction applied in the direction k. So consider that we can find by use of the Moore integral the displacement under the influence of the unit force. As well, we can find the displacement under the influence of the external load. By the same way, and of the first the first factor in the numerator is the diagram of the bending moment under influence of the unit force in the direction we look for the displacement. But the second factor in the numerator of this integrator we integrand is the load, external load under which we look at the displacement in the direction number y. So this is a use of Moore integral. We actually can, if we have the analytical equation for the bending moment diagrams, we can just do the analytical transforms and find this integral. But for practical needs, we can use the rules. We can use, for example, the rules of the so-called product of the diagram is done for the main system did of the assigned the diagrams of the bending moments for the statically definable main system, which did from the statically definable assigned system. So we can use, for example, widely very usable so-called Vereshchagin rule. Vereshchagin rule is not only one. Other rules can be for the practical needs. It can be the, for example, the Simpson rule for finding the integral of product of the diagrams of the bending moments, finding the displacement of the point definite direction under the influence of the force in the another one direction. The first is the direction we look for the displacement. The second is the direction of the applied load. And this is moments under direction of the unit force here and the external load or unit force as well. If you look for the displacement under in the first direction under influence of unit force in the first direction. So we can find by use of the Vereshchagin rule. As well, we can use sometimes the rule of Simpson and the rule, for example, of the trapezoid. Let's explain for the considered example. We have the formula of the Moore integral, considering the total of for the legs, one leg and another one leg of the considered main system of the considered frame. And for each, so this total is two summonses in the brackets here, two summons we have. And we can derive the denominator out of the brackets. This make it a little bit easier, the mathematical equation of the brackets. And in each summand in the bracket is a product of the area of the diagram of the bending moment. Definitely, we consider the displacement in the one direction on behalf of the force in the same direction. So we have to use the same diagram in the product in the numerator in the integrand. So what is the area of this diagram? The area is under influence of the. I will not explain how it is to find this diagrams. It's very obvious actually that we have the rod and under the influence of unit force, the rod length is arm is L, so the moment here is L equal due to product the force equal to one product rod arm L, so the moment is equal to L, and the diagram is linear. Along this one rod of the frame, this bending moment transmitted through the rigid connection of two rods in the corner. So we have the same, this force no longer increase the magnitude of the bending moment during this horizontal leg of the frame due to the force is parallel to this one segment of the frame. So in the brackets we have the area two segments, a first segment, a second segment, two summonds, and the factor outside the brackets is the denominator. We assume that for the definite one assignment that the rigidity, I mean the elasticity modulus and the moment of the inertia of section for each part of the frame are equal. So the 1, 2 multiplied by L and by L is area of this triangle, area of the diagram. L is one leg, another one leg L due to the moment bending under the unit force L. So this is area of the diagram multiplied by the fraction 2 third and multiplied by L. 2 third by L is in the projection connection have to be in accordance with the Vereshchagin rule. Vereshchagin rule, this have to be the magnitude or ordinate of the diagram of the bending moment in the same point of the x. Of x is the coordinate with for each of segment of the considered frame. The ordinata, this is abscissa, this coincides with the frame, starting from left to right. So, and the center of the area of the triangle is located here. Here located the two third part from this end and one third part from another one end. So for the linear form of the bending moment under unit force diagram, this magnitude is 2 third product by L. The same is for the upper one diagram piece of segment of the bending moment. So we have area of the diagram. Area is L. The length of this segment is L by the L. L is transmitted through the rigid point, the bending moment of unduring force from the previous one leg. This is the area of this diagram, and as it is distributed evenly here, I mean, the diagram is even distribution bending moment and the unit force for this one leg. So this is the ordinata under the center of the area of the diagram we got first, the area of the diagram and the location of its center of the area. It is in accordance with the Vereshchagin's rule. Vereshchagin's rule as well, I can remind that we can find it for the product of the diagrams, or just direct, if we have these diagrams in the analytical, as an analytical equation, we can do the mathematic transform. We can find maybe this analytical equation says this linear dependence of the bending moment and unit force on the x. This is linear inclined, but this linear is even distributed the bending moment. So you can do that, but we have as well widely used in the mechanics Vereshchagin rule is product this integral of more equal to the product of the area of the second one diagram by the ordinata of the first one diagram. First one diagram here, which in the projection connection correspond to the center of the area of the second one diagram. This is Vereshchagin rule. So, and after the mathematical transforms, we got that the displacement in the force direction under the force in the same one direction. This is a coefficient or factor on the canonical equations of forces method for considered main system here. These canonical equations we have two, because we have 2 times statically indefinable system, and besides of that we have the balance equations. But first we have to find the forces under the deformation, for the deformation of the considered, frame. So we do the mathematical transform, and the goal that is first factor of displacement under unit force in the first direction is the displacement in the first direction, like I summoned, is the fraction, the numerator, it's 4 multiplied L, the size of the arm cubed, and then denominator is 3 multiplied by the rigidity indexes of the frame, and considered one frame, this rigidity equal for each of legs. So this is the result. So what is the displacement in the first, in the direction of the application of the first force? First force is a force, unit force. If unit force is equal, we can find the factor for the canonical equation. Next, we considering the elasticity. Yeah, if we need to find the displacement under unit force, it can be not unit, it can be any magnitude, as well as another one force is subject to find what is the forces magnitudes. But this is displacement under unit force. But if we have the displacement under unit force, considering the proportional elasticity of the mechanical system, this product will be equal to the displacement under any force of the assigned or found magnitude. For the displacement under unit force, we can find the displacement in force direction and the force action in the second direction. So we have now 2 diagrams to have the product in the integrand. And as well, we have to remember that the displacement under second, under the unit force in second direction, the displacement in the first direction equal to the displacement in the second direction and the force in the first direction. This is the theorem of the reciprocity of the displacement. So displacement in one direction and the force in the second direction equal to displacement in the second direction and the force in the first direction. So we can find just together two unit displacement. Unit, we mean the displacement tangential of the unit forces in the displacement in the first and second direction, and the unit forces in the second and fourth direction. So to do that, we consider, for example, the first one, the left displacement of unit force and unit force in second direction in the fourth direction. This is as well using the more integral equality to the total of the integrals due to for each we have two summands for two legs of the statically definable main system. So for each leg we have integral, and the integrand are the fraction is the denominator, the rigidity of this each of the segments of the frame. But we have the same assigned for each segment, and we in the numerator have the product of the force. We have the product of the ordinata of the diagram of bending moments and direction of unit force in the direction of the first force, and the second we have which correspond to the center of area of the diagram of center of area of diagram of second force. This is in the projection connection. So we use the rule of finding this integral of Moore by the Vereshchagin's method. It's equal to actually we on the under direction of the unit force in the second direction, we don't have the bending moments in the first segment of the considered main system of frame. We have only the increased linearly the bending moment in the second segment of frame. This is, we have to put attention that the signs of the bending moments under the influence of the unit force in the fourth direction on the second leg, on the second segment of the considered frame, the sign is another than the sign of the diagram of the bending moments at the unit force in the second direction of the second frame. So for the summand in the sum of the first product of forces for the fourth segment of the frame is equal to 0 for the displacements 1, 2, and 2, 1, the lowercase letters, delta. And we consider only the summand for the second one segment of the frame. For the second one segment, we consider the area of it could be the area, for example, the unit force here. We have the right angle triangle. Excuse me, we have the rectangle here, and the evenly distributed bending moment along the area. This is L by L. We have the common factor of the rigidity minus sign due to this. These two diagrams are the opposite signs when multiplied to plus by minus equal to minus. So, and the center of the area of this bending diagram, we got the area, the center is in the middle of this one segment. So for the linearly distributed bending moment of the another one unit force, the diagram magnitude in the middle is if maximal L and linearly distributed, so we have the L divided by 2, the ordinate of the diagram of the second considered effort. And finally, we have the magnitude of the factors of delta lowercase 1, 2 and delta 2, 1 equal to by the reciprocity of the displacement, considering the theorem in two directions considered together. And this is the result. So next is the finding of the displacement and the unit force in the direction number 2 and the displacement in the direction number 2 together. So to do that, using the Moore integral and the Vereshchagin rule or other rules can be found. To find the Moore integral can be Simpson rule or trapezoid rule or another one, or just analytical determination if we just assume and substitute here the mathematical equations for this one independence on the coordinate abscissa x for this definite one segment. Due to this segment is not loaded by the force in the direction number 2, but vertical is not only horizontal is loaded. So we have that for this one diagram, the area is equal to 1, excuse me, just the half product of the L is the length of this segment, and L is the magnitude maximal of the bending moment and unit force. Have a unit force here, but to this definite one point, the moment is equal to the one product by arm is L. So we have a minus L. Minus to the low direction it is rotating clockwise around this one definite point if we consider the point of the embedding for the statically definable mechanical main system. So, and we have area of this diagram, and the second is we have to, in accordance with Vereshchagin rule, to find the ordinata of the diagram. The ordinata of the diagram of the unit force in the direction we sort for the displacement. It is the same diagram because on the second unit effort in the second direction. So we have the same, and the center of area of the triangle is 2 third part from one side and 1/3 part another one. So this, according to linear distribution, this is magnitude is 2 third parts of L. Finally, after the substitute, we have the displacement and the factor at the same time in the canonical equation of forces method. We have L cubed divided by 3 by E is elasticity modulus, and the modulus and the moment of section of for the bending moment of the section of this definite one rod. Yeah, and we have to find the three terms of the canonical equations. Delta upper case 1F is a displacement in the first direction of the first unit force and the influence of the external load F. And the same for the second, the displacement in the direction of the second unit force, which we substitute instead of the cutout links in the statically indefinable sign system to have the statically definable main system and subject to find this x1, x2. This x1, x2 are not unit forces, but we have to find that just only the factors in the canonical equations. We assume that the factors is the factors of proportionality of displacement and the force is displacement under influence of unit force. And for the second one direction, we have to find the displacement delta uppercase indexes 2F under influence of the external load F. So the more integral we find for the sum of two legs in the fourth direction. We have to find the displacement in the fourth direction and the influence of the external load. This is the diagram of the external load. It's applied for the upper one leg embedded here in the middle, and the bending moment is distributed linearly from 0 point in the middle of the point of the application of the external load to the embedding. At the embedding, we have the bending moment. The stretch it is upper fibers. So this one definite one beam, and the magnitude of the bending moment is this load applied multiplied by the L divided by 2. L by 2 is the arm of the action of this external load relative to the embedding. So we have to multiply in the numerator of the integrand of the area of the force diagram. Where is 1, 2 F product by L divided by 2 is a bending moment L multiplied by L divided by 2 is the arm, the arm of yeah, and we have 1 second. 1 second is a factor due to the area of the triangle is 1, 2 of the production of two, if right angle triangle of two legs. And we have to, this would be the square. This would be the square of this one, the diagram of the bending moment, so under the action of the external force, and derive the common factor outside the mathematical equation, the rigidity in the denominator, and we product this by L. L is the ordinata of the bending moment diagram for this definite one place, which is in projection connection of the point of the center of the area of the triangle diagram of the bending moments for the external force. So, but as the diagram for the bending moment in the first direction of the unit force, the diagram is evenly distributed. So we have L. L is another factor in the numerator of this, and we have only one summand in the sum because the force do not act on the second one arm into the main system we do statically definable or the assigned statically definable system. So we have the final decision, which is the displacement in the first direction under the force, the free summand of the first equation, free summand and the action of the external force. I think we can find the free summand of the second canonical equation is using the Born integral, the total by the segments of the considered arm for the first summand have to be equal to 0 because this force, external force, do not lower the first one leg. The simplicity of these equations, you would please put the attention, highly depends on the how logical we determine the main system of the assigned. As we do determine logical, the mathematical equations for finding of the factors and the free summands of the canonical equations, finding will be the simplest. Yeah, and here we have as well the area, the previous one equation, the area of this one diagram of the bending moments and the influence of the external load. And here we have the mathematical equation as this one segment, just a half of the upper one segment of the main system frame. This one segment we can consider in the diagram of the bending moments and unit forces in second direction. We can consider as a trapezoid here, and we have that the location of the center of the area of the diagram of bending moment under influence of the external load F. But this is a formula in the brackets here. In this equation, the brackets here, the formula how to find the ordinate of linear trapezoid. If we have two sides of the trapezoid, and what is the magnitude of the trapezoid for the definite one place? A place is 1/3 part, 1/3 part of the half. So this half and 1/4 of the half is like maybe 1/6 part in the denominator, 2 and 3 is 6. So exactly, if someone is of interest, just this is finding the diagram of this triangle diagram, linear diagram of the bending moments and the influence unit force in second direction on the arm L. So what is its magnitude in the definite one point? Point correspond to the center of the 1/3 part of this half. Center of the area of the diagram of bending moments and the influence of the external force. Anyway, after the substitute, we can find that the displacement second direction of the cutoff connection when doing the main system of the assigned statically indefinable system. The displacement second direction is minus the fraction, the numerator we have 5 multiplied by F external force by L cubed as arm length of the upper segment of the frame. And the denominator we have 48 multiplied by E and I. E and I is the rigidity of the considered frame. So actually we can substitute this all magnitudes got of factors and free summits in the canonical equation here. And we can find next, we can find two unknown variables under the deformation of this mechanical indefinable system. And in the next, we can consider the main system under the action of this force external and the force got of the cut of the links. And we will have more 3 mathematical equations of balance. And we can find all other support reactions in the point A, like in the bending, like components of the resultant force, as well the components of vertical and horizontal on the abscissa projection and ordinate axes, and as well the bending moments in the point A. But very important is to do the verification. As properly we remember that for the verification of statically definable system, we usually consider the balance equation. So it could be the balance equation, so equality to 0 the moment. For statically definable, I just remind balance equations for the moment, but moment rotating the system have to be equal to 0. But no, but around the point which one we did not use in the defining of the support reactions. This is verification for statically definable system. What is for this definite one case? Yeah, we can consider the total of two displacements. This is like a abstract, generalized concept of the displacement. So we can consider the more integral and displacement in the assumed direction S. Direction we say S. Direction is abstract. This is a total of two directions. Direction in the first, for example, for the first canonical equations, and in the first direction of the cutout force and under the influence of two unit forces together. To do that, we have to have the diagram of moments of two unit forces. The second one diagram, this here on the figure 3.4.2 is a diagram of the bending moments of two unit forces considering together. So if we take the first one diagram and the second one diagram, and would we add this diagram together, we will have this one diagram. For the first segment of the frame, we have zero moment of the zero bending moment and action of the unit force in the first direction. For the second one, we have zero moment for the first. So when we combine this together, remains only the diagram of the bending moments and the equal and the influence of the first unit force. And for the second segment of the assigned frame and the main system got from the assigned frames for second segment, we have the diagram, which is the result of the total of the evenly distribution moment on the second segment of the frame and the influence on the first unit force, minus the linear distribution with another sign. So minus of the bending moment and action of second unit force. And we have the diagrams like that. This abstract concept of data used for the verification of the correctness of got factors. So values of displacement along the direction of the first connection are determined previously Here we found this 2, 1, delta lowercase 1, 1, delta 1, 2. We got before. And we can just find the more integral, and we can find the displacement due to the product of the diagrams of the moments in the in the abstract direction S, abstract direction, which we consider as a total of 2 directions displacements here. And we can find that for this one diagram, this one is of unit force, this one diagram is that the area of and the area of the diagram for the first second frame for the abstract direction of deformation S, not first, not second, but just as the sum of these 2 direction deformation is possible for the concept of the elastic proportionality and for the concept of the independence of action of all forces under the assume that the mechanical system is linearly elastic. So the area of this diagram we got before, the area is in the brackets here, 1, 2, this area triangle diagram, the product by the product by the arm of the product by the magnitude of the diagram of the same force in the point of which in the point of its center of gravity. So finally we have after the substitute of all factors, we in the force direction. Oh, I'm sorry. Excuse me, please. Yeah, I a little bit mistaken. We look for the displacement in the first direction under the action of force applied in the 2 directions together. So the second one is the product of the area of the second one diagram by the magnitude for the center of the area of the second one diagram, the magnitude we have from the first one direction as we find the displacement in the first direction, first direction, but 2 forces, first and second, 2 unit forces. So the magnitude of the diagram is L due to the in first direction the diagram is evenly distribution of the bending moment along the second one segment. So we have that this more integral equal to the fraction in the numerator 5 product by cubed L cubed and then the denominator 6 in the rigidity indexes of the frame. And if we will consider previously got 2 displacements and the influence in the first direction and influence on the first and second unit forces, we can do do the total and find the same result. So we assume that we found the factors for the canonical equations correct. Sum of displacement along the second, we can do the same as we can find the total in the abstract on behalf of the action of the unit force, abstract unit force in 2 directions together. The force in the first direction, the second one, and how does this abstract force acts in on the displacement in the second direction. We do the same as in the first one. So we find the product of the diagrams of the area of the diagrams of the abstract force in 2 directions together, unit force in the first and second one. But we product this on the diagram, product by the diagram ordinata of the diagram of the bending moment under influence of the force unit force applied in the second direction. So we do that as we have here only one segment, due to along one segment, the diagram equal to 0. This simplify a little bit the determination of the product of the diagrams. Using the Moore integral, we can find that considering the opposite signs of these diagrams and the magnitude negative relative to this one area is positive. So we have only one summand in the Moore integral. Using the Vereshchagin rule finding the product of the diagrams, we find this diagram area, and for the definite one point of the which corresponds the center of area of this diagram, we have to find the ordinata of the diagram corresponding the location along the axis x for this definite one leg. Second, we have to find the for this one same location, find the magnitude of the diagram M2. After the finding the magnitudes and this is one third part is here because the location of the center of the area is close to left one point of the segment. Two third part from the right and one third from the left, and we consider the another one diagram. One third part is one fourth of L of linearly distributed magnitudes. And after the substitute this all into the Moore integral using the Vereshchagin rule, finding this product of the integral of the integrand as a diagrams product, we find that it is equal to minus, in the numerator we have 3 cubed, and the denominator 6, and the indexes of the rigidity of the frame. And the same we can find as we got from the previous one, delta 1 2 delta 2 2, the displacement and unit forces in the first and second directions and the second unit force. And 2 1 1 2 is exactly because we assume the reciprocity of the displacement in the when we change the indexes, they are the same. So finally we have together minus the same fraction as we have here, and even more than that, we can do the universal verification. Verification is important, so we put so much attention as we can. The generalized abstract displacement 1 and 1, 2 and 2 on behalf of the action of two unit forces 1 and 2, 1 and 2. So to do that, we use the only we use only this diagram in which is a total, which have to be total of the diagrams of the bending moments and direction of the first and second, and we consider that as only for the one summand as we have, because other one equal to 0, and we finally have that the displacement in S direction under the assumed force in the same direction is the fraction of 2 in the numerator multiplied by L cubed and divided 3 and the rigidity indexes, and we can consider previously to got the totals of the delta 1 1 plus delta 1 2, and here delta 2 1 delta 2. We can consider these two magnitudes we have the results here, and we find that together they are 2 in the numerator, 2 multiplied L cubed divided 3 and the rigidity indexes of the frame. And the same we can do for the check of correctness of the finding of the free summands of the canonical equations, this correctness we can use. How do the what is the force? We assume the abstract as a force, external force impacted the displacement in the abstract s direction into two together displacement in two directions. This is a total of these two directions, delta uppercase 1 under force F plus delta uppercase 2 force F. And we have got here delta uppercase force F. We have got here, we have delta uppercase. We have got here, but to do the check, to verify correctness of finding the delta uppercase, we can consider this direction, use the diagram got for the total of the diagrams of under the unit of bending moments under unit force 1 and the unit force 2. We got together the diagram M and for the S index is a total of the two diagrams. And what about if the force acts in this abstract direction S? We cannot indicate it in the draft what is the S direction, but just just algebraic total of directions into absent cutoff links when we created the main system statically definable out of the statically definable assigned system. And we can find using the Vereshchagin rule. Vereshchagin rule can be as well, can use the trapezoid rule, Simpson rule, or others approaches, or just analytic determination of the product of the diagrams. But very usable Vereshchagin rule, we consider the area of the action of the external load and the area of the bending moment diagram, and product this to the ordinata for the definite one point of the center of area of the bending moment diagram of the assigned external load. To find the abstract displacement in the S direction under this load, we have this would be the total of two summands of the canonical equations. This will be the product to this one diagram of the bending moment and unit forces taken together in two directions, and assuming that is a action in the abstract direction number S. So, and when we do product the diagrams, this is in the brackets area of the diagram of the force of the external force, and this is the magnitude of the diagram of the bending moments in the on the unit forces action in the abstract S direction, to these two factors on the right from the brackets. And we have finally, after the mathematical transform, that this under the given load, the displacement in the abstract S direction, this direction is corresponds to all into two directions, first and one, just the algebraic total of them. This will be the direction, displacement and direction of the external load, like in the numerator F multiplied by L cubed divided by 48 and the index of rigidity of the frame. And the same we can get just by the total of the got before delta uppercase 1 F and 2 F we got before the displacement in the first and second direction under the influence of the external load for the main system. And this will be the same when we consider these two got before, and when we determine by use of the more integral and the Vereshchagin rule of the diagrams product. So questions and comments. The main system of a statically indefinable frame. When we substitute, first of all, we have to determine the number of the static indefinability of frame, and to understand how many the deformations compatibility equations we have to use. So this number satisfies the number of the equations in the canonical equations. The main system is a statically definable system, which we have when we cut off the unnecessary connections of the sign static indefinable system. Unnecessary in the sense of this geometric interchangeability. So when we cut off this unnecessary so-called connections, the assigned system is become to be the statically definable. This will be the main system, but at the same time it remains geometrically unchangeable. 3.4.2 system of canonical equations of forces method for doubly statically indefinable. We have two canonical equations for doubly statically indefinable mechanical system, and we have two unknown variables known as the forces, and we have the factors for each variable in each canonical equation. Factor is a displacement and the joint force of the action in the considered direction for the definite one equation in order in the system of the canonical equation. And the second is the second index is the index of the effort we considered, which one behalf the displacement in the considered direction. The effort as well can be as many efforts of unit of the loads instead of the cutoff links. And we have in each canonical equation we have the free summands for each summand for each equation is a displacement in the each direction corresponding the number of the equation in the system under the action of the assigned external load. 3.4.3 determination of the coefficient of canonical equations of forces method using more integral of displacement in the direction of replaced connection identity forces applied to the direction of each replaced connection and the displacement in this direction of replaced connections and the action of applied load. And to find the factors in the canonical equations and find the displacement at the action of the assigned load, we can use the so-called more integral. The interesting integral is because it is the total of the for each of segments of mechanical system and considering the intervals and variable along each segment of the mechanical system, and this for each the number of the summands in the integral more is equal to the number of the segments of the mechanical system main system, and for the canonical equations finding factors, and the each summand in the more integral is itself integral, and integrand is the fraction in the in the numerator we have in this fraction we have in the numerator of the fraction in the integrand of the integral more we have product of two diagrams. One diagram for of unit force and the direction we have to find the displacement which in, and the second factor in the numerator of the integral more is the diagram, the ordinate of diagram of the bending moment, and for each of the leg, for each of segment in the limits of the segment of the mechanical system. To be honest, to be sure, the more integral can be used not only for the displacement under the action of the bending moments, it can be the displacement under the action of the shearing forces and the longitudinal forces as well. Yeah, but it's not subject of the considered example. Usually the displacements under action of the shearing forces and the longitudinal forces in the mechanical system we can neglect as they are of the minor importance. Displacement of the bending is by the magnitude are, um, are dominant, so it's not so important to consider as the displacement. So anyway, the product of the diagrams, one diagram on the direction of the displacement we sought, we defined direction under displacement under determination. And the second diagram was the diagram of the force, maybe a diagram of the bending moments for the bending, which is the cause of the displacement. 3.4.4, finding the more integral of displacements from unit forces and form a specified load. By multiplying diagram using Vereshchagin's method, we can practically we can use or just a direct product of the diagrams of the bending moment in one bending moment diagram under influence of unit effort, unit force, and the direction which in we look for the displacement. And the second diagram of the load under which we look at the displacement of the mechanical system. But for the practical needs, we can use some rules developed to do that. And one is Vereshchagin rule, Vereshchagin method. As well, we can use Simpson method, Simpson trapezoid, widely used trapezoid method and Simpson method for definite cases, exactly, with definite, in each case, for definite assumptions. And about Vereshchagin method, we have to have the diagrams, the bending moment, if we do about the displacement under the bending, not under the shearing or longitudinal elastic deformations. For the bending, we have to have the diagrams, one diagram of the unit force under action of the unit force in the direction which in we look for the displacement, and the second diagram of the bending moments and the action of the external load for main system, statically definable main system. The use of more integral to check the correctness of finding displacement and the unit forces coefficient of the canonical equations of the forces method and the action of the specified load by determining and using the total diagram of bending moments from all unit forces. Yes, so very important for practical needs to check correctness finding the factors and the free terms of the canonical equations. To do that, we can consider the so-called abstract directions of the displacement. So we can consider displacement in two directions, just algebraic total taken together. So if we put it together, to do that, we have to, for the use of, for example, more integral, first we have to have the common diagram of the bending moments of the main system and the common action of unit forces. This is usually not difficult to do this diagram, but this common direction of the action of two unit forces is an abstract concept due to the we just use a algebraic total algebraic sum of magnitudes of two vectors. Actually, these vectors of the forces or maybe moment vectors are directed in the arbitrary, not arbitrary, but directed in the other directions. We cannot, from the geometric point of view, the vector point of view, we cannot find the total of the vectors if the magnitudes if they're directed in the other direction. So maybe some vectors are the forces components, and some vector can be the bending moments, for example. Yeah, but from the approach, considering the mechanical system as linearly proportional elastic system. So we can do that as we can consider this abstractly as we can consider this displacement independent in abstract concept, and this force is actually an abstractly in the same linear total. So thank you very much.